Have you ever been there trying to get up to speed on something complex, maybe for work, or just because you're curious, and you're just drowning in information, wishing you had a shortcut to, really getting it?
Oh, absolutely. It's a
Yeah.
common feeling these days.
Well, that's exactly why we do these deep dives. Today, we're digging into something called chain of agents, or CoA. It's a pretty exciting development, making AI models, well, way smarter and more collaborative.
It really is a leap forward.
Our mission here is simple. Pull out the key insights from the latest research on CoA for you, give you those aha moments without you having to wade through everything yourself.
Get you right to the good stuff.
Exactly. So let's set the scene a bit. We know large language models, LLMs, and these multi-agent systems where different AIs team up. They're pretty amazing at tough tasks, right? Like deep research or complex math.
Definitely capable.
Hmm.
But they've always had significant drawbacks.
Right. Like, imagine trying to manage a complex project, but your team members keep talking over each other, or they can only do things exactly by the book, step by step.
Yeah, very rigid. That's been the issue with traditional multi-agent systems.
Yeah.
They can be, frankly, inefficient. Lots of redundant back and forth, computationally expensive.
And hard to adapt to new things without someone manually tweaking all the instructions, the prompts.
Exactly. That manual prompt engineering is a bottleneck.
Yeah.
And then you have other methods like TIR, tool integrated reasoning.
Yeah, where the LLM uses a tool, like a search engine, follows that sort of think, act, observe loop.
Which is fine, for basic tool use.
Yeah.
But it doesn't really capture that dynamic, complex teamwork you need for really hard problems.
Okay, so that's the problem space. Where does chain of agents fit in? What's the big idea?
Well, this is what's so fascinating. Chain of agents, CoA, it's a completely new way for an LLM to reason. It lets one single model handle complex problem solving from start to finish.
Yeah.
It does this by dynamically activating different tools and even different role-playing agents within itself.
Hold on, within one model, so not separate AIs talking.
Precisely. Think of it like having an entire expert committee, a whole collaborative team, but it's all happening inside one super efficient brain.
Wow, okay. An expert team in one brain. I like that. So break that down for me. What kind of roles or tools are we talking about inside this single model?
Great question. It really mirrors how a human team might work. You've got two main types: the high-level coordinators, the role-playing agents, and then the specialists who execute tasks, the tool agents.
Okay, role-playing agents. Are they like the project managers, the strategists?
Exactly. You have, for instance, the thinking agent. That's like the overall orchestrator, keeping the whole process on track, making sure the solution makes sense.
Got it. The big picture person.
Then there's a plan agent. Its job is to take a complex request and break it down into logical steps. Like, okay, first we need to search for this, then analyze that web page, then generate some code.
Makes sense. Step-by-step planning.
And crucially, there's a reflection agent. This one's really interesting. It's like the internal critic. It looks at the progress, spots potential issues or inconsistencies, brings together different pieces of information, and helps refine the plan.
So it can self-correct. That sounds powerful.
Very. And finally, a verification agent acts like quality control, checking the reasoning and the outputs against certain criteria to make sure it's actually correct.
Okay, so those are the thinkers, the internal consultants managing the process. What about the tool agents? The doers.
Exactly. They're the specialists that get called upon. You've got a search agent that knows how to craft the perfect query for a web search, like best AI breakthroughs in 2024, optimized for results.
Rather than just a generic search.
Right. Then a crawl agent can go to a specific web page found by the search and pull out the relevant information.
Okay.
And maybe a code generate agent that can write a little snippet of code, say Python, and run it safely to perform a calculation or analysis.
So the key difference here is that all this planning, execution, reflection, checking, it's all happening seamlessly within the one LLM instead of needing separate models to chat back and forth.
That's the core innovation. And it's why CoA avoids the big problems of traditional multi-agent systems. You eliminate all that computationally expensive chatter between agents. The token consumption just vanishes for internal communication.
Ah, so that's where the efficiency comes from. No need for messages flying back and forth.
Precisely. Plus, it allows for genuine end-to-end training. The entire system, all these internal roles and tool uses, learns and improves together as one unit.
Okay, that makes a lot of sense. It sounds incredibly efficient. But how on earth do you train a single AI model to be this multifaceted, to wear all these hats?
Yeah, that's the million-dollar question, isn't it? It involves a really clever two-stage tuning process. The goal is to create these highly capable models, which they call agent foundation models, or AFMs.
Agent foundation models. Okay, AFM. What's stage one?
Stage one is called multi-agent distillation for agentic supervised fine-tuning. It's a bit of a mouthful.
Huh, yeah. What does it mean in simple terms? Distillation.
Right. Think of it like this. You take existing, really good multi-agent systems, the paper mentions one called O-agents, as an example, systems that are already proven performers.
Okay, the current state of the art.
Exactly.
Okay.
And you have them solve a bunch of complex problems. You record how they did it every step, every decision, every message passed, the whole successful thought process or trajectory.
Like a detailed log of a successful mission.
Precisely. Then you take these successful logs, these trajectories, and you carefully convert them into a format that this new single AFM model can learn from. You're essentially distilling the effective problem-solving patterns, the wisdom, from the complex system into the single model.
So you're teaching the AFM by showing it examples of expert teamwork.
That's the core idea. And it's not just any examples. They use a really rigorous four-stage filtering process on this data
Why filter so much?
to ensure quality. They filter out simple tasks, tasks where the original system gave wrong answers or had messy outputs. They specifically enrich the data with examples where the model reflected and corrected itself.
Ah, so learning from mistakes is key.
Very much so. They even upsample trajectories where errors were caught and fixed. The resulting training data is really high quality, focusing on multi-tool use in these long, complex reasoning chains like 5 to 20 steps, much deeper than typical training.
Wow, okay, so that's stage one. Learn from the best distilled examples. What's stage two?
Stage 2 is agentic reinforcement learning, or RL. This is about further refining the AFM's abilities, really honing its performance, especially for achieving the final goal successfully over those long chains of reasoning.
So practice makes perfect, essentially.
Kind of. They give the AFM challenging problems, things it can't just answer from memory, and then they use reward functions to teach it what a good outcome looks like.
How do they define good? How does it know it's right?
It depends on the task. For web tasks, they might actually use another LLM as a judge to say, yep, that's correct, or nope, that's wrong. A binary signal. For things like coding or math, the reward is based on getting the answer right and having it in the correct format.
Okay, so first learn from experts, then refine through rewarded practice. It sounds very thorough. Does it, actually work? What are the results like? And this is where it gets really exciting, right? Because the performance numbers they're reporting for these AFMs, they're pretty stunning.
They really are. These agent foundation models are setting new state-of-the-art results across almost, I think it was 20 different benchmarks, diverse tasks.
So not just a one-trick pony. Get this. On a web agent benchmark called GAIA, one of the AFM models, specifically an AFMRL 32 billion parameter one, hit a 55.3% average success rate.
Which is notably better than the previous best, WebSailor, which was at 53.2%.
And on another web task, HLE, that same AFM got 18% success, which was actually better than some systems using the much larger GPT 4.1 model.
Yeah, that's a significant result, showing strong capability even compared to much larger, more general models in specific agent tasks.
And it's not just web stuff. How about coding?
Impressive there, too. On Live Code Bench version 5, AFMs got a 47.9% pass at one rate. That means getting the code right on the first try nearly half the time.
Wow. And math. That's always a tough one.
Definitely. On a really challenging math benchmark, AME 2025, the AFMs achieved a 59.8% solve rate. That's a huge jump. 10.5% absolute improvement over the previous state-of-the-art.
A 10% jump in advanced math reasoning. That's massive.
Overall, across various math tasks, the AFM-RL32B model averaged 78% accuracy. Again, significantly higher than the prior best for models of that size.
So let's just pause on that. You're telling me we have an AI system built with this CoA approach that's topping the charts in complex web navigation, contest-level coding, and advanced mathematical reasoning.
That's what the research indicates, yes. A remarkable breadth and depth of capability emerging from this single-model agentic approach.
Okay, my mind is slightly blown. How is it doing so much better while also being supposedly more efficient? That feels counterintuitive.
Right. That's one of the most compelling parts. Remember how we talked about eliminating the interagent communication? That translates directly into massive efficiency gains. The research found that AFMs cut down the inference cost, basically, the amount of computation needed to generate an answer, measured in tokens by an incredible 84.6% compared to traditional multi-agent systems.
84% reduction. That's huge.
It's enormous. And they also tend to use fewer external tool calls to get the job done. It all comes back to that unified architecture. No wasted effort on internal chat. Everything is streamlined within the model.
Lean and mean, basically. Okay, efficiency makes sense now. But there was something else really interesting about generalization, using tools it hadn't seen.
Ah, yes. This was really surprising and cool finding. They took the AFM that was trained only on code and math problems.
Okay, so specialized training.
Right. And then, at test time, they gave it tasks that required using tools that had never been trained on. Things like a web search tool or even a visual inspector tool.
And it could use them how?
It could, as long as it was given very clear, strict instructions on the format it needed to use to call those tools. It could correctly figure out how and when to use them to solve the problem.
Just based on formatting instructions, that implies something deeper is learned, doesn't it?
It really does. It suggests that the rigorous training, especially the kind needed for precise code generation, might instill a more fundamental understanding of how to structure interactions and follow instructions,
Hmm.
which then transfers to unfamiliar tools.
That's fascinating. So precision in one area leads to adaptability in others. Did the web-focused agent do the same?
Interestingly, no. The web agent, while it often made the right calls to unseen tools, it struggled with the exact character-level precision needed in the formatting, suggesting that maybe the code math training enforces that structured interaction more strongly.
Huh. It's like the difference between giving vague instructions versus a precise recipe. The code agent learned the recipe format.
That's a great analogy. And speaking of getting things right, they also found ways to squeeze even more performance out of these AFMs after they've already been trained.
Oh, how does
Well,
that work? Like giving them more time to think?
sort of, yeah.
Yeah.
They explored techniques like best of three, where the model generates three potential answers or reasoning paths and then picks the best one. They call it AFM BO3.
Okay, like having a quick internal review.
And another one called AFM Pass at 3. Here, the model gets up to 3 attempts to find one correct solution for a task.
So if at first you don't succeed.
Try again, basically. And these strategies provide a really substantial boost. Remember that GIIA web benchmark where the base AFM got 55.3%?
Yeah.
Using pass at 3, so allowing 3 attempts, the score jumped to 69.9%. That's a massive 14.6 percentage point increase. It significantly outperformed what other models achieved with similar pass at 3 strategies.
Wow. So just letting it have a couple more tries makes a huge difference at the top end. It's like us double checking our work or rethinking an approach.
Exactly. It shows there's still headroom to improve performance even post-training by using smarter inference time strategies.
Okay, let's try and wrap this up then. What's the big picture takeaway for everyone listening?
Well, it feels like AI is taking a significant step forward here. We're moving beyond just answering simple questions. This chain of agents approach allows a single AI to genuinely tackle complex, multi-step problems, almost like a coordinated team would.
Right. It can plan, execute using different tools, reflect, verify all internally within one model.
And it does this with remarkable efficiency, slashing computational costs compared to older multi-agent methods. Plus, it's achieving state-of-the-art results across a really diverse set of challenging tasks: web navigation, coding, math.
And showing these surprising abilities to generalize, to use tools it wasn't explicitly trained for, which is very promising. And the great news is, for anyone wanting to dig even deeper or build on this, the researchers have open sourced everything, the model weights, the code, the training data.
Yeah, it provides a really solid foundation for the research community to build upon. It's definitely not the end of the story.
Absolutely. This feels like just the beginning for these kinds of agentic foundation models.
Which leads to a really interesting thought to leave people with.
Go on.
If one of these AFMs can effectively embody an entire team of experts and tools, what happens? What new kinds of incredibly complex problems could we tackle if we started combining multiple of these powerful agent foundation models together? What does that next level of collaboration look like?
Combining the teams, that really opens up possibilities, doesn't it? Something to definitely mull over. Keep asking those questions, keep exploring, and stay curious.